Hi, welcome to the inaugural WasmEdge community meeting, recorded on the 5th of October 2021. To kick things off, let's head over to Haidai.
I think the first thing is to review our 8.2, the release. So first of all, I want to talk about the mission of this release. Actually, in this release, we find before this version, we just focus on the Linux operating system, and we just on the AMD 64 and ARC 64, these two architecture. However, we found lots of use case is not just only on this platform. So in this version, we open to focus on other operating system and other architectures. So first thing is that let's talk about our WasC feature. Our WasC now can run on the Windows and Mac OS, including the M1 model and the Intel model. So also we have the pre-built Mac OS binary, so you can just try it on your operating system. And the second, let's talk about the WasC socket. This is very important feature in this version because when we enable the WasC socket, now you can open a socket on your Wasm program, and also you can send some bytes and receive some bytes. So you can communicate with other sockets. You can do some, the TCP streaming or the UTP message. Yeah. And this feature is, I believe in this version, we only enable on the Linux platform. And we will need some time to port this feature, on Windows and Mac OS because there are just a little bit different API on these, the Windows and Mac OS. So it will on our feature roadmap. And the third thing we want to talk about the WasmEdge C API, which is different from the Wasm C API proposal. The Wasm C API is just an API to integrate our WasmEdge runtime. So because our mission is to do the cross-platform support, so this C API in this version, we just enable the HF, which is the 32 bits environment architecture support. And we also integrate our Wasm C API with the proxy Wasm. It's a very, I think it's a very cool proposal and very cool spec. So you can search more things about that. And we just working on pull request to add our WasmEdge into the proxy Wasm C++ host. And the fourth thing, I want to talk about the ahead of time features, because we found that our ahead of time compiler just enable the CPU related optimization options. So it will a very strange thing will happen. That is, you compile your Wasm application on a machine with CPU type A, and then you just copy the file to another machine with CPU type B, and it just not work. So we just want to provide a new option to disable the CPU related optimizations to avoid this situation. If you want to deploy your WasmEdge with, if you want to deploy your Wasm application on the different CPU types, you can enable the generated binary options to disable these related optimization options. And last feature is that we add very simple Rust bindings for our C API. is called WasmEdge sys, which is just use the Rust bindgen, just FFI mapping, just map our CAPI header into Rust source code. So it will, look like very not so developer friendly, and we just working on it to increase the development experience. Yeah, so that's our feature part. And we also fix two important issues in the WASI function, because we are working on we actually finished the integration with the Quick.js, so you can run your JavaScript application in our WasmEdge. However, before we port this, we integrate this Quick.js, we found the two file system WASI function is implemented wrongly. So in this version, we just fix these two WASI functions. Yeah. So that's our review of the 0.8.2.
Thanks, Heide. That was a great wrap-up of WasmEdge 0.8.2. Now, you mentioned the WasmEdge Networking Socket API. Next up, we have Michael, who's going to actually do a WebAssembly Networking Socket demo. Take it away, Michael.
And networking sockets is actually one of the what I consider a missing feature and a crucial feature for using WebAssembly outside of the browser. Because if you look at a lot of use cases, outside of the browser, like using it as a runtime for microservices and things like that, you almost always need to access networking somehow. And if you don't have this capacity, you would have to write some other host application outside of WebAssembly to do this for WebAssembly. So that has always been a pain point. People have to write all this code that's to provide this functionality to embed web services in, right? To embed WebAssembly in. So the community has been looking at this for a long time. People want to add the standard Linux or POSIX networking library into WebAssembly, and it's called WASI socket proposal, right? But that has been very slow. Things progress around that. If you search the internet, you find a lot of complaints. That's people are talking about. That's why the features of WASI are not complete. But a lot of them are referring to that spec. So instead of waiting for a resolution in the official spec proposal, we decided to implement this feature based on the current discussion that happens in the WASI socket spec community, to implement this feature on our own. And so we're happy to announce that's in a 0.08.2. That's we have now implemented this for both Rust and JavaScript. So I want to give you guys a little example. So I want to share my screen so you guys can see it, right? That's the screen I shared. Okay.
Yeah, it's good.
Yes.
Okay, great. So yeah, we're building socket functions into our runtime. So from the WebAssembly bytecode application, you can now create network sockets and then make network calls. But then as an application developer, how do you use that? Because it's not yet a WASI standard. So you can't just use the standard networking interface in C, C++, or in Rust yet, right? Because because the upstream compiler doesn't yet support that. So we need our own API to do that. And our Rust API is in this repository, second state / WasmEdge WASI socket, and there's an example directory, and you can see there are a couple of example files. But what I would show you is, say, the HTTP client. And if you go to the source code, you're going to be able to see how to do it. So there's some, as you can see, there's some very simple APIs. There's a package called HTTP request, and then you can just do get, you can do post, and you can do things like that. It's not, it's not the default Rust network API, but it's close enough, right? So this is a new API that you can use in your Rust application. And once you compile your Rust application into WebAssembly and run it on WasmEdge, you will be able to do this. You would be able to do this HTTP, networking. And let me show you another example that's on the server side. You have a similar API, and you can do things like, create a HTTP client, handle HTTP connections, and listen for HTTP connections, and things like that. So you can read through this application. Essentially, this application opens up a TCP listener and then pass out the results to see if it's HTTP, and then handle the HTTP request. So that allows you to do to write an entire HTTP server based on WasmEdge, right? That's just imagine the potential use case here, because one of the things, the other work that we have also done with WasmEdge is make it OCI compliant, meaning that it cannot be orchestrated and managed by by Kubernetes, right? So using Kubernetes and a service mesh, you will be able to start a WasmEdge application, and this WasmEdge application can listen to the network, and now it becomes a microservice, right? So it's become more and more like a complete service framework. So this is a Rust API. I just want to mention it briefly, and then you can also see the JavaScript API. I think it's here, yeah. So it's in the repository second state /WasmEdge-quick.js. And there's an example.js directory, and there's a file called http://demo.js. And what it does is that it's we further package this Rust API into a JavaScript module. So you can just import those HTTP operations from the HTTP module in the JavaScript package, and that allows you to do very simple things like get, post, put, patch, and delete, right? So those are the basic HTTP, the basic 5 HTTP operations that we typically want to do in a JavaScript application. So that's so this is so there are two APIs. One is for Rust, and it's give you more complete control over the TCP/IP, the TCP connections and HTTP, and then there's this JavaScript APIs that's essentially it's wrapped around the Rust API we have just mentioned, and gives you more convenience. But yet there's still one problem, as you can see in all our examples, if you pay attention, we are using numeric IP addresses. We're not using domain names. And the reason for that is because at current, we are just we just implemented the basic networking layer, so it can only resolve IP addresses. It doesn't have those DNS functions. As you know, there's a big news about DNS yesterday, right? The Facebook misconfigured their DNS, and their entire network went down. I heard, that's they had this problem of because their internal communication is also based on DNS, so all their internal networking, all their employee work was done. So so there's there's story of people using chainsaws to open up the server cage in order to change the DNS inside Facebook. Because, crazy stories like that. But anyway, there's so at this current, we can only do HTTP, we can do HTTPS, and we can only do the numeric IPs. So because of that, we have a couple issues in the WasmEdge repository that basically says, let me try to find it. Where is it? So now we have so many issues. Let me see if I can.
Michael, you can use the filter.
Yes. Sorry.
Okay.
Yeah.
Great.
Like it's brute force work. That's so this issues 388. We are I think we already have someone working on it. That's Mr. Ma is working on it. So what this one does is that this gonna put a new host function into the system that does DNS resolution, and we're gonna once this work is done in the Rust API and in JavaScript API, we're gonna be able to support DNS, right? So that's so when we see a HTTP address like that, we would go to call this host function first to resolve into numerical IP address and then do it, right? So that's that's the approach we are taking. But then you can imagine there are a lot more work after this that can be done. For instance, HTTPS. Do we support that? That's we imagine that can also be supported in both ways, through either a host function or through the perhaps through the WASM crypto standard, which is another project that we're working on, is to add cryptographic extensions to WebAssembly, right? So both ways could work, but it's the faster way is probably go through another host function again to support HTTPS. So those are the features that we are looking for the community to support. So if you are interested in things like that, come to this issue to discuss, or come up with some demo applications and share with us. So yeah, that's on my side.
Thanks, Michael. Yeah, that was really interesting. So I guess that's similar to the Kubernetes ingress, having that domain name resolution, but not only from external but you have that as internal services, like you can have internal IPs and ports talking. One thing that's really interesting in this is creating processes which maintain state. So that's a really interesting thing. That's implementing a database layer or a storage layer that can then communicate over its natural ports and things like that. So yeah, there's a lot of really good potential work in that space. Thank you for that. Excellent. And so we have had the review from Heide and the networking socket demo from Michael, and we have Michael and Heide next with the future features of WasmEdge as a discussion. So you guys like to take it away with that, the future features of WasmEdge?
Yeah, maybe I can talk a little, and then Heide can talk about it. There are lots of very interesting features we plan for the next release, and one of the biggest is to make. As you have heard from Heide, that's WasmEdge already runs on in this version runs on many versions of Linux and Windows and macOS, and including the M1 processor, right? We wanted to run in more application scenarios, in particular in embedded OS and real-time OS. So we work with CL4 SEL4, which is a Linux Foundation project that creates a real-time operating system for automobiles and things like that. And so we are getting really close to make it to completely working on that platform. That would give us the first a real-time platform access. And as you can imagine, one of our follow-on talks today is to talk about TensorFlow and AI inference on the platform, right? This is one of the crucial features that's needed in autonomous vehicle. When you have autonomous driving, you need you need something like that. You need a container, and you need AI inference. That's one of the big things. And we have 4 WASI proposals that's currently WASM proposals that's currently working. Maybe Heide can talk about those a little more. Including the WASI sockets and things like that. WASI crypto. Sorry, I keep getting names confused. And then and then in this release, I think this is after the OA2 release, that we have a new install script that makes installation of WASM WasmEdge much easier. It's now become just one command instead of going through a whole process. That's the script that works on all the flavor of Linux that we tested, and also on Mac as well. So that's one of the usability features that has really improved. And I also like to point to an article and a video that we shared yesterday. That's is to run WasmEdge in Dapper. Many perhaps have heard of Dapper. It's one of the very popular open source project coming up. In the past, I think mostly in the past year, and it's a microservice framework. It's developed by Microsoft, and it's open source, of course, and it's also now in CNCF incubation. So it's I would say it's like a service mesh, but it's not exactly. But it has a sidecar concept. So it provides a framework for applications to run as sidecars, as microservices, right? So it's so it can support, say, native applications or Node.js or Docker and things like that. And what we did is make WebAssembly another runtime for it. And that's also why the socket proposal comes so important, because the way we do it is that we write a little web server application around WebAssembly first, and then put embedded WebAssembly in it, which is nice, and I think solves a lot of problems that we have today. But a more complete solution, I think, would be for WebAssembly applications to stand on its own as a sidecar. There would be no assistance from from outside actors, right? So that's one of the directions we're working toward. So that's where we're hopeful. So those are the some of the features on my side. So Haidai, do you want to add other features that the team is working on?
Well, I want to extend the SCL4 part, and currently our our SCL4 integration is just, it will build an 16 architecture image, and we can just use the QEMU to to run this demo. However, our next step is to to coating the whole ecosystems and on a Raspberry Pi. So this is our I believe this is our very important step to to try some use case and real-time system. So so I believe the SCL4 part will will have a very interesting progress in, and I believe is in this or next month. Yeah, so this is the first thing I want to talk about, is about the SCL4 part. And also I'm very excited that we have 4 interesting proposals, which is the first one is to implement the WasmC API, yeah, which is just different from our WasmEdge API. Yeah, so this is the first thing. And with this WasmC API, we can just embed our WasmEdge into many existing tools. Yeah, so this is first proposal. And the second one is we want to enable the crypto functions in the Wasm. For example, you can just we just want to enable the WasM crypto proposals in our WasmEdge. So we can just enable something like the OpenSSL features in the WasM applications. So that's our second proposals. And our third proposal is we want to enable the signature part in our WasmEdge tools. which means you can sign your WASM applications, you can verify the correctness or the correctness and the size and any metadata on your distributed WASM application. So that's our the WASM signature part, and our last part is to to enable our WASI proposal, which is a very abstract layer, allow you to to run AI inference with a given model. Yeah, so that's our 4 interesting proposals that that we are working on. Yeah, so I think that's all from my side. Thanks. Yeah.
Okay, thanks, Haido. Yeah, that all sounds very interesting and very useful. And I think we're going to do a Q&A now, an all-in questions and answers. So I guess the floor's open in that sense. And if anybody has any questions, anybody on the team or externally, anybody watching?
I think Shiwa wants to talk about, how to use our TensorFlow extensions, right? That's one of the things he wants to talk about.
Yeah, I would love to talk about that. So I came across WasmEdge probably last month, and I got actually I had raised that issue regarding the M1 not actually installing. So I had connected with Shreyas from the community, and that sort of led to creating the build scripts for M1. So that was really great to see a lot of progress being made on that front. So I was particularly interested in exploring the TensorFlow extensions. So currently, with the QuickJS implementation that we have that is provided by Second State, we have extensions for TensorFlow and TensorFlow Lite. So I have been regularly contributing to a lot to TensorFlow.js. Now that is basically the web version of TensorFlow running on with JavaScript. And as runtimes, there are a lot of different supported runtimes right now for TensorFlow.js, namely with WebAssembly, with WebGL, and then also with WebGPU. So those are the 3 standards. So basically, my question was, in case we want to create an extension for TensorFlow.js as well, with that is supported with WasmEdge. So generally, what you'll have is with like a normal TensorFlow implementation, like whenever you're having an extension, you'll have like, let's say, an .h5 file. With TF-Lite, we have a .tf-Lite file. So normally in TensorFlow.js, what happens is that all your model configurations for a machine learning model are sort of stored in a model.json file. So I mean, I have understood like how the implementation of like whenever we embed the JavaScript within the Rust, and I have gone over the TensorFlow example and the TensorFlow Lite example that have been provided. So my question to the team, and specifically like Tim as well, because Tim had also reached out to me via email when I had put up the proposal, that how can we implement another extension specifically for TensorFlow.js? And apart from that, basically the second thing was, would this require like folks from TensorFlow team itself to also probably come over, or what would that integration look like? Like what should be the steps? Because I did try to sort of go over it, sort of dig deeper into the integration that is already there for TensorFlow and for TensorFlow Lite, but I was sort of finding it hard to find the right kind of steps through which we're able to support or add the support for TensorFlow.js. Because today TensorFlow.js is becoming quite popular. It's like it has more than 15,000 stars on GitHub. So it's a really popular way to also use it. Not only like directly in native JavaScript code, but also since we do support Node.js as well, being able to run WasmEdge on Node.js. So there is also a potential opportunity to embed it over there. So just wanted to know, like, what do you think might be the steps and how can we do that?
Yeah. So at the moment, sorry, Michael, looks like you're gonna.
Yeah, that's perhaps Tim, you can go first. Yeah.
So at the moment, we use the native binaries. So it's in a WASI-like fashion. So what we do is we enable the TensorFlow to execute natively on the system. And we actually call that through the runtime. So we have specially, essentially pre-programmed that functionality into the system. And it's very much optional, but it's a great feature. We do this in other ways. We use some other native libraries to do things like language translation and optical character recognition and things like that. And we call it this WASI-like implementation, because whilst we're very much, like, we're 100% on board with the WASI implementation, the WASI standards, that's all happening in a certain fashion, and it has a certain amount of governance, things like that. At the same time, we'd like to experiment with what's possible, and so we've gone ahead and implemented those WASI-like features in quite a number of things. So I guess from your angle, I was looking at something the other day which is similar, which is SQLite compiled to JavaScript and as a standalone WebAssembly executable. And that's interesting because it comes with a variety of different nuances. So in the case of the SQL implementation as a WASM binary, there's things like, you have let's call it like a run. So you execute the WebAssembly. What you have to do in that instance is you have to load all of your data into that run, and then you perform the functionality that the SQLite provides. And at the end, you have to export all of your data before the end of the run. And then essentially, like with, as you know, with WebAssembly, once that's executed, there's no persistence. So there's that to get around. But I guess in the case of TensorFlow, it's very much like you load in your data, the model runs, and then it always gives you back. So you're not really having that issue with that, storage persistence, that sort of thing. So I think it's a really interesting use case. And one of the other things that we always try and focus on, or at least acknowledge and address, is that when you're doing any sort of edge computing, like when you're running this sort of functionality for cloud or for edge, we try and get the process and the data as close together as possible, because whilst we have extremely fast execution times and all these performance benefits from WebAssembly, if we're sending huge amounts of data across a network for execution, then that becomes the greatest part of the round trip, and it's no longer lightning fast. It's your upload and download is actually the bottleneck. So there's some interesting challenges. And then these layers that we've put on top, for example, with our RPC work, we've actually managed to say, all right, well, let's have it so that the WASM execution, so that the WebAssembly runtime actually does a remote fetch for us on the server side. So rather than the client having to perform any sort of high bandwidth, high throughput, we just say that the client or the requester can just say, hey, I want to perform that WebAssembly function. And then the server side actually goes off and does the remote fetch, brings in the data, executes it, and then returns back. And in some cases, it's interesting, like with TensorFlow, all you want back is a yes or a no or a word like, hot dog or banana, or, true or false or something, or even 1 or 0. So there's those interesting nuances that are worth thinking about. I guess starting with your use case, like what's your ultimate goal? What's your ultimate use case? And then how can we build the architecture to suit that? Does that make sense?
Yeah, that makes sense. So, I mean, according to you, like, what can I do from my end, at least to, like, if we were to get this rolling in and add the support for the TensorFlow.js extension, what can I start off with?
Yeah, I guess we could go back to the, and Michael could probably have a speak to this, the JavaScript work that we've currently implemented. So we're actually integrating the JavaScript and WebAssembly, which is the path that I was going to take with the SQL. So did Michael want to, sorry, we both started talking at the same time, but did you want to speak to that as well? And then perhaps Heide can.
Sure. Yeah. So, that's, so like Tim said, our current approach with TensorFlow is really to use the native library and then wrap it in WebAssembly, and then wrap it in, the APIs like, the Rust API and the JavaScript API that we have all go from that, come from that stack, right? It's going down all the way to the, to the native library that can utilize the GPU and all that. And TensorFlow.js is another approach. TensorFlow.js essentially compiles TensorFlow into WebAssembly itself, so it doesn't go the native route. And then it has a JavaScript helper outside to do that, to call the WebAssembly functions and all that. And I believe we can compile, TensorFlow.js, the WebAssembly module should be able to run on WasmEdge as well, because it runs on V8. If it runs on V8, it should run on WasmEdge. It's just no one has tried it. I think perhaps this is one of the directions that you can start. Because we already have a Node.js add-on. It's called an API for WasmEdge. So we already knew that WasmEdge runs in the Node.js environment as a V8 alternative. And can we, make small changes? Because I haven't really looked at TensorFlow.js, how exactly it works, but I just know underneath it uses WebAssembly to do that. Can we, go into TensorFlow.js and change the runtime engine from V8 to WebAssembly, to WasmEdge? I think that would be the first step. The obvious trade-off here is that to run it this way, it's going to be a lot slower than run it our way, because our way we go directly to the native library and do it, right? And now with TensorFlow.js, you essentially running it inside WebAssembly. And the reason for that is also where TensorFlow.js was designed for the browser use case, and in browser you can't break out of the browser to run core native applications. You have to stay inside the browser. So that's why they did it, right? That's but on the server side, things may be different. But that's so it could be a little slower. I think it could be if you run TensorFlow.js in the browser, you typically see response time like this and this, so it's like half a second delay, 500 milliseconds. So it's very difficult to get a very continuous, smooth. Say if you have a video and you continuously want to recognize the cars on the video, you can't really do that with TensorFlow.js, but you can do it with our other approach that use the native APIs, right? But TensorFlow.js, I agree. A lot of people use it, and it's a lot of people have already built applications on it, and it'd be nice to have it running in our system as well. So so I would say the way to start is to go into TensorFlow.js. I haven't looked at it really closely, but you can go there and look at it and see where is the handoff between JavaScript and the WebAssembly. Where does JavaScript, when you call a TensorFlow.js function, you're doing it in JavaScript, right? But underneath, it goes to call a WebAssembly module. Where does that happen? And if you find that point, then you can find the WebAssembly module, and you can try to run it in WasmEdge. And that, I think that's be, our, build approach. Yeah. So if you want to work on it, I would encourage you to raise the issue on the WasmEdge repository, and so we can track it, right? So other people can look at it and discuss it with you as well. So that's.
Yep. And just one point, Tim, if it's fine, like I just had one point.
Go. Okay.
Yeah. So Michael, as you mentioned regarding mainly TensorFlow JS running on the browser, but of course there is also dedicated APIs for running it with Node.js. So it uses the just-in-time compiler functionality of the Node.js to run faster and much more heavier models as well. So if that's something we can also explore, because as you mentioned that with WasmEdge there's support for Node.js. So if that is also some like that area, like not just from the browser side, but also on if you're wanting to run Node.js on the server side, basically, that is something that we can also definitely have a look at.
Yes, and we have another advantage here is that like you said, there are optimization for to make it run faster. It's JIT, right? And that stems from the V8 history in the browser, because in the browser you typically use JIT optimization, but we're on the server side, we can do AOT. So in that regard, we could run a lot faster than V8. So so maybe we can make TensorFlow.js run a lot faster. So it's just nobody has tried. Yeah. So
so I can create an issue.
Yeah, that's really interesting. Thanks. That's like Michael says, raise an issue and get some more eyes on it. And I think getting some input as much as we can from those sorts of other projects and organizations is really good. I've found with the work that we've been doing with this is a lot of the time there's this method that's being used. Like, for example, when you're using TensorFlow with Python, it works in that context. It works really well. But as soon as you try and step a millimeter out of that really rigid implementation, it becomes extraordinarily difficult, and you're digging for information. So in your case, you're going to go and see, oh yeah, they just instantiate the module in the browser and then they run it. And then you're like, how does that happen? And then you start digging. So I appreciate it's going to be a little bit tricky, but I really would love to see you have a good look at that and have a deep dive into that. It'd be very interesting and very useful, but it probably won't be easy. So best of luck, and it'd be very, very cool to see what you come up with.
Yeah, because that is like the reason I sort of reached out, and it was so great that at the time when I was looking at this, the community meetings just got started, so it was sort of a perfect timing for me. Yeah, but I'll raise the issue, and like if I can, I'll probably start on this front that you mentioned, Michael, and like, I mean, if there can be any support from the team as well, that would be really great. I'll start off by first creating the issue and just laying down the entire requirements that that we have. Yep. All right.
Yeah. Awesome. Thank you. Yeah. Fantastic.
Okay, I think we have Shiraz at the chat. He wants to ask about.
Yeah.
The performance.
Hello.
Yeah, go ahead. Yeah.
Yeah. So just a small doubt, or if I can get an answer from a noob perspective, how does our stack-based VM competes with the other already implemented VMs that are based on WebAssembly guidelines?
Yeah. So well, we have a paper, but the paper, as you mentioned, that's the issue with all those research papers is that in order to publish them, you need to have a hypothesis and a methodology and all that. You have to narrow down your scope. So it's not a comprehensive, I would say, performance comparison, right? But we are looking at more comparison, and I think someone in the community has done it. So I can't find the link right now. Vivian, do you have the link? The guy who did the computer algorithm benchmark and added all the WebAssembly stuff in it. So there's a website that has all these algorithms, and they mostly compare programming languages, right? Python, they have Julia, they have all kinds of programming languages, like tens of them. That's there's a guy who expanded that and added all the WebAssembly runtime, including in both interpreter mode and in IoT mode and in JIT mode, right? And so they have a huge list of all those things with all those different algorithms. So that's one resource we can that we can look. That's I don't have the link right here, but I'll find the link, and when we post the video, I'll put the link up there. And so that's one area, but that's also still I would say basic computational algorithms. Those are just like an n-body problem, or compute some sequence of numbers, things of that nature. For more real-world applications that you would have to look into issues like WASI performance and like the things we just talked about, TensorFlow, and things like that. In order to do that, we need more complete applications to do benchmarking and comparing, and we don't have that right now. And we know our performance are pretty good when it comes to things like AI inference and TensorFlow, just because we use the C native libraries directly instead of using an interpreter, right? So we can have performance that's similar to what you would get from the C library, so. But we'd love to see more performance studies in this area. That's so if we can encounter applications, that's, I think TensorFlow.js would be a great example, because that's one of the more sophisticated application, and we can compare head to head with V8. That's because it also runs on V8, right? So it's so things like that we'd love to see more contribution from the community. So I can't really say for certainty that we are in a complex application scenario, how much better we are against our competitors. But but from the basic benchmarks that people have done, both from us and from third parties, I would say we'll perform pretty well. That's and also our approach for more complex libraries bodes well with performance. That's because we are calling those C functions directly from WebAssembly instead of using WebAssembly bytecode to simulate the same functionality, right? So yeah, that's so it's a work in progress. I would say it's encouraging, but a lot of work still needs to be done in order to make this happen. Yeah, so I think we will post the link in the chat. You guys can look at it. That's it's programming language benchmarks is one of the I think well-known benchmark sites. And this guy did all those WASM implementations and created a fork, essentially a fork that has all the WASM runtimes. And you can see, sometimes we perform very well. It's benchmarks both the memory use and the computational time. So you can see in some areas we perform well, and sometimes we don't. Sometimes our interpreter works well, sometimes our AOT works well. So but in general, I think we perform pretty well. So.
Thank you for answering.
Okay.
Yeah, thank you to you both. That was really good questions, interesting, good comments. Anybody have any more questions? Because I think it's a really good idea to flesh out some of the details of these implementations and new ideas or anything like that. Any comments? Anything you potentially want to raise as maybe need a bit of help with, or the next thing you're planning on working on? I'm looking at so implementing persistent execution across runs. So that's something that we find really interesting, and it's obviously a big deal with WebAssembly because as we know, it executes in that ephemeral sandbox environment, and so that's always a real sticking point. Is for a program to be useful, it kind of has to have a memory, have some form of storage over, even if it's a millisecond or a second or a minute or permanent. There's got to be some form of memory there and storage. So that's something that we're looking at always, and we've implemented it in a few different contexts, right up as high as like at the API level, at doing secure HTTP requests and hanging onto information. At the moment, one of the things that we've done successfully is we've managed to, right from the request side, is store information in RocksDB, because that'll just accept raw byte arrays. It will just put it straight in, and we're able to convert that, actually push it through the WebAssembly runtime and into the RocksDB database and then back out again. And so that's something that's been on the cards for quite a while and we'll continue to work on. So I guess with these, like with your TensorFlow work there, Shiva, you're looking at, like I was saying before, you just ask it a question and get an answer back and then it's done. And that's useful for you. You can then store that information in a third-party site that's calling it, or in the app or something like that. So we're trying to add a lot more richness to the WebAssembly environment without stepping outside of the security boundaries, if you will. And it's interesting. It's the nature of the beast. You have these excellent features of security and safety and performance, and then you have to start massaging them into a useful, but it is very early days, isn't it? This is only years old. It's not something that we've been working on for a long time. So yeah. Anybody got any interesting little ideas or projects or?
Yeah, so like just an interesting thing that we have the Cloud Wasm Day coming up. So I'll be speaking at the Cloud Wasm Day, although virtually sort of giving a demo of the WasmEdge with TensorFlow integration.
Nice.
So just wanted to share that.
Yeah, awesome. We saw that. Appreciate that. Yeah, that's great. Yeah. So we're gonna have two WasmEdge related talks in the Cloud Wasm Days. I'm gonna be there in person. So yeah, that's.
Yeah, excellent. So no other questions or anything like that?
Yeah, about I'm actually implementing a Python API, which is essentially a C Python using the various wrappers for C Python functions. I'll be implementing this, but to do it right from the ground up, I need some help in uh, constructing the WasmEdge modules, the objects lying beneath them, like how should any person access them, what should be the callables and other stuff.
So I'll just repeat that question. So you're looking at doing from the ground up a Python implementation, and you're wondering about at the VM level how to. So it was a bit hard to hear. Sorry, it was a bit crackly. So you're wondering, do you have some help with at the lowest level in the VM how to call? Is that? Am I hearing that correctly?
Sorry, am I audible correctly right now?
Sorry.
Am I audible better right now?
Yeah, that's good. Yeah.
Yeah. So the question was a bit different. I'm essentially developing a wrapper around the existing WasmEdge using the C Python implementation. C Python provides a lot of API calls for the Python interpreter, and I'm wondering how, from the ground up, how exactly should I design it? Like, what should be the callables, different callables, and how should I correctly sandbox the WasmEdge modules and other stuff?
Okay.
Right. So maybe I can talk a little about it. I understand you are working on the Python SDK, similar to our, say, Go SDK and Rust SDK, right? So what I would do is to start from the design. How does it look like in Python first? So what would be the API that makes most sense in Python, and then think about how we're going to implement that, right? That's because one of the things that we don't want is to make the Python API look like C API. Then the Python developers, because the whole purpose of doing that is for the Python developers to make it easy to use for the Python developers, right? If we make it easy to implement and just map the C API, into Python, the Python developer comes to say, oh, that's what is this? It doesn't look like Python, right? That's the exercise we went through with the Rust API. Is to first, the principle is to first come up and see how a Rust developer, or in your case, how a Python developer would use it, and then write it down. This is what we want the API to look like, and then to go find how to implement in C, like you said, C Python. That would mostly involve integration with our C API, right? That's so in Python you call our C API. You may find things that are not yet implemented in our C API, or not yet supported in our C API. In that case, we that's what GitHub is for, right? That we raise an issue on the GitHub, and then we discuss whether this is really needed, and whether which version do we put it in, and things like that, right? So I would say we start from a design of the Python API first. When it's finished, what is going to look like in Python, and then from there to say what are the C APIs we needed to support that.
Yeah, that's a great idea. Did that answer your question okay?
Yes, that did answer it. Thank you.
Right. And just to add to that a little bit, one thing that Michael and I have discussed in the past is when we're doing things like this is probably most relevant to the TensorFlow work, is if you just do things in really tiny incremental steps, because the trick is to find, because you're dealing with different language barriers and different APIs and different implementations, like maybe there's a gap, or the way that you will move data, there will be some process that you'll need to execute. And so when you implement something, you sort of like tick that off and say, okay, that's okay. Or you reach a point where you have a certain amount of data, or data in a certain format, or the ability to like move to the next step. you kind of need to stop and document that. And then when you move to the next step, if you hit a hurdle, it's good to break it up into tiny pieces, because if you come to the GitHub and with like a really specific request of, I need to execute this against that API and this is what my data looks like, that makes it a really clean way to ask a question, and then for developers to satisfy that requirement and then to move forward. Because when you look at these things, sometimes it's so big, it's there's too many things to address at once. So I think, yeah, that's right. Start from one end and then start really small increments and be really explicit about what you're doing, how you're doing it, what the data looks like, what you're trying to call, what happened when you called, what you get back. If you break it down to that, it makes it more enjoyable as well, because you feel like you're getting somewhere. You're just ticking off tiny increments, but eventually that's a good approach. I think when you're dealing with really complex system across languages and across data types and things like that, it's good to really chunk it down, break it up into small pieces. Yeah. Thanks, guys. Great questions. So no other questions for now? Okay, thanks everyone. Thanks so much.
Thank you. Yeah.
Okay,
thanks.
That's a wrap.
Thank you.
See you next time.
Thanks, everybody.
Thank you.